experiments in the field. And so it's really a pleasure to be here. She's the acting director of the Division of Particle and Astroparticle Physics at the Max Planck Institute for Nuclear Physics. So thank you so much, Manfred, for being here. So it's really a pleasure for us to host you. Take your time.
Okay. Can you hear me? Yeah. So thanks for the kind invitation and the nice words. Actually, I call myself a theorentalist, which is confusing because working both sides, you get them if people put you always on the other side sometimes. This talk today is about the theoretical side, and I like to focus on conceptual problems, conceptual developments. So, and that's about the fact that, in some sense, we need to think in new ways about how particle physics, the so-called standard model, makes sense ultimately. The standard model itself is an extremely successful theory. I was said any of the inventors would have lost any bet how good it works in a way which is really remarkable, classically in symmetries, but also on the quantum level in a way. But if you look at it from a distance, actually, it's the success story of some very strong concepts that he put in, generalize. The starting point was quantum electrodynamics, which was at the time the most precise theory ever, where electromagnetic effects were described at 10 digits beta comma g minus 2, etc., ways which no other theory could do. So it was natural to generalize, and generalizing the U1 symmetry, gauge symmetry to SU3 color was then quantum chromodynamics, which also has been very successfully confirmed. So it was obvious then to continue and go on for the full standard model to this gauge group. You don't understand which group, but that was the way it went. And then it's where we are. There were some new ingredients here, namely that you need a scalar, a fundamental scalar Higgs particle, and the so-called spontaneous symmetry breaking, the famous Mexican hat, a word no longer allowed in the US. By the way, I know a guy who sent an application to NSF and he was sent back. You should change Mexican hat into wine bottle or whatever. Didn't accept the application. Still, so the Mexican hat. So it's all based on four-dimensional quantum field theory, symmetries, and quantum effects. And there's really excellent agreement with the experiment, but there are known deficits. And these known deficits make us believe that there's some beyond the standard model physics. So these experimental facts hint some problems. First thing, the electroweak scale is much smaller than the Planck scale. The fourth interaction, gravity, is still missing, and gravity has the Planck scale, 10 to the 19 GeV built in. Well, this is all at 100 GeV, so it's 17 orders of magnitude in between, and hard to understand how the scales can be so far apart. We'll come back to that. If you look at the gauge couplings of the theory, they run on the quantum effects, and they run at high scales together to a precision where I say, oh, there's something, so-called grand unified theories, but then they miss at the card level precision, they miss each other, which means there could be some other physics to contribute, but also then the physics were in bed. The other thing was that neutrino masses were discovered to be finite. The textbook standard model doesn't have that, so you can amend it. There's different ways, simple and more complex ways to do that. We don't know which one's the correct thing. And I was surprised that the mixings, unlike the quarks, that are huge, big, maximal particle, etc. Of course, then there's the whole flavor structure. 3 generations of quarks and leptons have mass and mixings, which are just parameters of theory. But then if you look at them from a certain perspective, they realize there are some patterns, regularities that cry for some explanation that we don't have. So that's why a lot of the flavor problem is one of the problems that's out there. Another problem is the Baranoff symmetry of the universe. If you have a hot Big Bang, you make particles, antiparticles, essentially the same number, and they would annihilate and would essentially produce photons. So we'd expect that only light has survived and not matter, us. And this is called the Baranoff symmetry of the universe, which is something the standard model itself cannot predict in numbers, even though it has all the ingredients, but numerically it's off by many orders of magnitude. Then there's dark matter. We learned that 95% of the universe are different from the matter we know, 30% about dark matter, 27%, and the rest is dark energy. So the matter we are, the stars that we see, are only 5%. We're on top of something else that actually requires to be discovered. On the theory side, there's problems, so to say. The standard model does technically, mathematically, simply not exist without a cutoff. It's a so-called triviality problem. I will come back to that. That's on vacuum stability. It doesn't make sense. And it makes sense by saying if you embed the standard model in something else early enough, then it makes sense. So there is some argument that you have to look at this. Then there's the gauge hierarchy problem, namely connected to the scale separation. How can it be that scales are so far apart? And I will discuss this, so say, first in simple ways, but then in real solutions. There's Gauge unification and charge quantization. It's hard to understand why quarks and leptons have identical charges up to some 1/3, 2/3. There's no need for it to be unless there's some unification to some bigger picture. There's also the so-called strong CP problem. We don't understand why quantum chromodynamics doesn't violate CP at a much larger level. And of course, the unification with gravity is missing. And when you go on, the fact why the three generations are there, why which representations exist, why the four dimensions, etc., and so on. And it can go all the way on. And I think there's also experts here working on things like string theory, which is that it depends how far you want to go. There's lots of problems, well motivated from the situation we are. So it's really amazing because there's this very successful theory. On the other side, there's so say all these problems. But then on the experimental side, you go ahead and build experiments to test it. And this problem, so say all these problems have made progress in the last years. Very nice. There's many ideas, experiments where I can test. And this one problem, this gauge hierarchy problem, where the situation has actually become worse. The point is, so we did expect at the LHC that the physics connected to that will show up. And the answer was that it did not show up. It's not there. So of course not a problem if there's a certain theory it is not confirmed in the experiment. But what I'm trying to explain is that it's not just a problem of one theory, it's a generic problem that we are facing, which requires generic solutions. Don't get me wrong, I want new machines like the FCC, but of course it's like also when you invest into some new experiment, you should ask yourself, what's the motivation to do it, right? Is there a guarantee that something will be there or not? I was heavily involved actually in the LHC proposal, so there was the argument that unitarity, Higgs-like state, and even more could come, but now it's again the same discussion in a somewhat different situation. The problem is essentially a scale problem. There are different scale problems, and in four-dimensional quantum field theory it goes as follows. You start off with a Lagrangian, maybe the standard model in four-dimensional quantum field theory. You write down the symmetries and the particles, we are representational symmetries, and then you theorize some parameters, masses and couplings, and they're consistent with, as long as they're consistent with the symmetry. Like a photon is massless because there's gauge symmetry, but otherwise you can put in numbers as you like, etc., as long as you're consistent with the symmetry. Then you can ask the question, are vastly different parameters a problem? You have a theory with different parameters, let's say masses, can I make vastly different numbers there? And the answer is why not? Classically, it's not a problem, it's just a parameter of your theory. Just take it as an input parameter and forget about it. At the quantum level, it's per se also not a problem because, of course, quantum effects will shift your parameters to the physical quantities, but that's it, so be it, etc. So the question is, should I worry about three-level parameters if they are very different? And usually we would say no, because you can take what's called the Born approximation. You can take a starting point of your theory and do quantum calculations, go to another point and find the shifts. Born approximation means that you can go there, start the perturbation again, and with the shifted parameters and walk backwards or somewhere else. So starting from a classical Lagrange is nothing special. It's just the expression that's your perturbation point, and the change is just a parameter change. This is all fine up to the point when you do see a problem. When you talk about vastly different physical quantities which are connected by quantum effects, if there's same operator structures there, they talk to each other, then of course there is a problem because they tend to affect each other. So the scale problem that we are talking quantum field is the problem of operators, quantities with the same quantum numbers that do affect each other. That said, you can look at the standard model, so-called hierarchy problems. And it's the stability of vast different scales on the quantum corrections. And the way people formulate it is actually nonsense. If you take the standard model with a cutoff lambda, then people say you would expect that the Higgs mass should be at the Planck scale at 10 to 90 GeV, because there's a high scale should be pushed up. That's the way you write it. The Higgs mass squared gets corrected by some lambda squared in this combination, and lambda is much bigger, so that's it. It's of course nonsense because the standard model is renormalizable, a renormalized quantum field. There is no cutoff required. The cutoff is just in your brain if you want, so there's no problem. If you talk about such a cutoff, then it only makes sense if you mean implicitly some new physics, some other physics, so say, not a regulator, but a physical scale that comes in as affecting things. And then, of course, there's not one scale because then you have thresholds, different particles. It's much more complicated than this relation here. So this is not a problem as long as you stay in the standard model. The problem comes when you go beyond the standard model. There's more. We know by now that neutrinos are massive. If you make the standard model neutrinos Dirac neutrinos, you just add your Kaber couplings, not a problem. It's just like the standard model, chirosymmetry, everything is the same. If you, however, invent Majorana neutrinos, as many people like, because then you get tau beta decay and other effects, lepton number violation, then there's a problem. because it generates another hierarchy problem. The Higgs mass corrections go proportional to your Kawa coupling squared over 16 pi with the loop effect times m squared. Taking the seesaw relation for the masses and the parameters in between there, you find that this scale m should be less than 10 to the 7 or 10 to the 8 GV to avoid the problem. And that, of course, then immediately gets into trouble with other ideas like that to explain the Barnard symmetry via leptogenesis. Then there's immediately a clash there that's coming up, etc. But the main problem is this up here, this lambda squared, etc. So what's the real problem? The real problem, really in elementary terms, is the problem of two or more scalars. The standard model has just one scale, all masses are proportional to that, so there's no problem, period. That's really all the discussion about the hierarchy problem of the standard model is simply nonsense. The simplest case where the problem shows up is if you have vastly different scales of connected operators like two scalars, little phi and capital phi, with mass little m and capital M, and a hierarchy in the parameters between m and m. Vast different masses. Then both phi dagger phi and capital phi dagger phi are singlets. So they must interact via portal term. You cannot avoid, there's no symmetry forbids such a term, that the two scalars talk to each other because they have the quantum numbers, in addition to the self-interactions they have. So this lack of symmetry allows a term which must be there so that the two guys talk to each other. And when you calculate quantum corrections of the light mass, then they are automatically driven to the heavy mass. So you don't understand how this relation would be stable under quantum correction. If you start like this, it makes whoop and it goes up to the heavy mass. And that's actually the core of the hierarchy problem, that you have two scalar operators which are dependent in this way. So why is the problem then? Well, if you talk about standard model embeddings to solve any of the problems that we discussed about, then usually you're forced into new symmetry breaking and new scalars. So it's, for example, if you do gauge extensions, left, right, symmetry, Patsalam, guts, etc., they all must be broken because we don't see them. So you need some Higgses in the game. So there's a standard model Higgs and another Higgs then, right, at high scale. Or if you take SUSY guts, the same thing. Supersymmetry was invented to solve the hierarchy problem because there are systematic cancellations between fermioning and bosonic contributions. But it comes back when you embed these guts into guts, so say, so-called doublet triplet splitting. You don't understand why a doublet and triplet component are so far apart. It's also in many of the fashionable Higgs portal scenarios that people discuss in dark matter. It's the same problem. When people argue for light dark matter these days, they have exactly that problem. How can there be light dark matter while there's the Higgs up there, right? It's a stability problem. So I call this a conflict between indications for beyond the standard model physics and the fact that you have more scales. That's where the conflict sits. So not just one model is generically. If you can do some new physics without a new scale, then you're sort of fine. But as soon as you start talking about this, is a problem. And the point is that essentially any problem that we know which makes us to extend the standard model requires an extra scalar. So it's a clash of concepts, you can say it this way. Now, you can say ignore it or do something about it. Now, as I said at the beginning, the situation has actually become worse. We did expect that there's some new physics to be seen at the LHC. The standard model problems was a strong motivation for PSM physics, and having the Higgs mass or the vacuum expectation value plus the hierarchy problem, there was a strong expectation that some new physics must show up at the LHC at TeV scales. New particles should have shown up at the LHC beyond the Higgs, supersymmetric, whatever, composite, etc. It's just a simple scale ratio when you do this kind of exercise that what you would expect. Now, experimentally, neither SUSY or any other TeV composite state has been observed so far, up to a few TeV. So what's wrong? The clash of concepts shows up in experiment, right? It's not clear. And that's been termed the little hierarchy problem, that the next PSM scale is too far away from what we understand, so say, not 10 orders of magnitude, just at least a few orders of magnitude, to the point where it's uncomfortable. And this amplifies the old hierarchy problem. It's not that you just find some theory that makes you go to a few TeV and then you find a way to go all the way to the Planck scale. No, there's a problem already going to the next scale before you even talk about the Planck scale. So that means you must solve this little hierarchy problem first. And the trick to go is to say is that the symmetry, you can use symmetry, then with all scalars, including Higgs, eventually are Goldstone bosons or pseudo-Goldstone bosons. Goldstone boson is connect to symmetries. If you make them connect to symmetries, they have a chance to solve the problem because the Goldstone boson decay constant then has a relation to the new scale lambda, which allows to relax the relation a little bit. In so-called little Higgs models, this was actually amplified in a certain way by not only having the W and Z boson be Goldstone bosons, but also make the normal Higgs a Goldstone boson, a pseudo-Goldstone boson, and that way the scale problem gets reduced. That's what people did. There was sort of a fashion a few years ago, and then people studied various realizations. The problem with that is you essentially technically solve this little hierarchy problem, but you shift the problem because the new theory at 10 TV had again scalars and didn't solve the big hierarchy problem. So it's just reshuffling the problem without solving it really in some sense. And that's of course a possibility, but not what you want. So that was the situation before we did something more on that. In addition, there are indications in the standard model that something special is going on. It goes like this. If you look at the standard model, where cutoff has no meaning, there's one thing is triviality, namely that the quartic coupling, if you do nothing, goes higher and higher and it explodes, the so-called lambda poles. And if the lambda pole is real, then it's a problem. It's a mathematical inconsistency with the so-called Shell-Neyman spectral representation. So that's why people said maybe it's not there, it's just perturbative. Lattice calculations over the years have shown that it seems to be there. Then the only way out then is to say there's some scale of the physics where you have to embed to avoid that problem. And if you do this exercise, you can plot the top mass versus the Higgs mass and ask yourself how far can you go before the problem occurs at a scale lambda. So if you take the lambda to be TeV, and you get this wedge here, anywhere in between is allowed. If you go to the Planck scale, this little wedge is left. That's a long time ago. Then meanwhile experiments have happened. The top mass has been found here, and the Higgs mass has been found here, and it turns out to be exactly in that little window here, in this wedge here, which is amazing. It's not only in this wedge only, it's actually exactly at the lower end of the wedge. And this wedge can be seen in the following way. If you take the coupling of lambda, the Higgs coupling lambda here, and run it to high scales, it goes in the lambda pole. That's the upper end, it's the bound. If you're on the low side, it tends to go down and become unstable. The potential flips over and creates an instability, vacuum instability. The vacuum would have been unbounded from below. For mysterious reasons, this number is extremely close to this blue line here, this lower point, where it almost tilts over. And this is a relation that's connecting completely unrelated parameters of the standard model, the top mass, the Higgs mass, running gauge couplings in a way where you say, well, is there something special? Is there a message in that that's being told? So there's an important conspiracy between numbers, and it's a remote. It's inspiring because this is not the quadratic divergences; it's a log divergence. The running is beta functions, log divergence. So there's a miraculous relation between logarithmic evolution in the standard model, which the parameters seem to tell you. Okay. Now we have talked about the quadratic divergence initially. Now we talk about the log divergence. Is there any way to connect that? Well, the question is, if you ask yourself, is there a message in this miraculous log cancellation so it can be interpreted? Remember, in the standard model has only one scale, called mu. It's the one single scale of the standard model has a special role. If in addition, mu squared would be zero to what I just said, the potential, the Higgs potential would be zero, would be flat. So the Mexican becomes flat by quantum effects. This running to zero, this point where you are, means that this famous Mexican head at the time when you read the high scale is flat. Everything's gone. So that is inspiring to turn things around. Say, maybe I should take a flat potential, means only gauge kinetic terms, to start from high scales and run it down and generate my standard model symmetry break this way. Means that the Higgs would be essentially some composite state, a Goldstone boson, pseudo Goldstone boson of something else, etc. And you can ask yourself, what is it then? Well, it's here talking about the limit, which is the conformal shift symmetry limit of the standard model. Because there's only one scale in the standard model, this is the VF mu or mu squared. If that goes to zero, then there's no scale left in the standard model whatsoever. Means that you start then from a theory with no scales, which is in some sense tempting. Because if you had an ultimate theory where you had to put in some numbers to explain things, you would say, why these numbers? Here's the other way around. The theory would then have no number to begin with. All numbers are a quantum effect, and only ratios of numbers become observable, predictable quantities. That's the direction you're talking about. So that's why we said, let's try if we can make these conformal ideas in the context of the standard model more explicit and address the situation as we have it. So if you talk about UV conflusions and conformal symmetry, you have to make up your mind in some sense. Because a successful theory should have a meaningful completion, means that the beta functions vanish. Scale invariance means that the beta function eventually gets zero. There's two ways to do it. There's the so-called trivial fixed points where couplings run down, going flatter, 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 like in non-abelian gauge theories. And there's the interacting UV fixed point where it goes to some number and gets stuck there and stays there forever. If you have interacting UV fixed points, it's quite a challenge because there's only one coupling. All the couplings of the theory have to run in such a fixed point at the same time and avoid lambda pose and instabilities, etc. This requires a very careful selection of particle content, where you then are stuck with why should nature choose such funny combinations of particles to make that happen for you? Of course, you could turn it around and say maybe it is an argument that explains the particle content from that kind of argument, because so far nobody understands which particles are realized in nature. It's just we copy them from what we see in experiments. The easy one is the so-called trivial fixed point solution here. There's no fundamental scalars, there's no Yukawa couplings, it's an asymptotically free, non-repeating gauge tree. That's sort of easy compared to that. So we decided to go for the second route. And then we did something which is just combining elements that in principle are there to address these problems. It's a combination of so-called little Higgs ideas with conformal UV completions. So the idea is that all scalars, including the Higgs, are Goldstone bosons or pseudo-Goldstone bosons. There's some symmetry that's broken, so it's a global symmetry. That the scale that we talk about where things are matched together is about 10 TeV, as little Higgs models do it, so it's beyond the LHC. Nothing was expected to be seen. There's a symmetry expression for the little hierarchy problem, and all the couplings, lambda and Yukawas, essentially dissolve. Means if these scalars that we talk about are all composite particles, and in a trivial fixed point means that all the effective couplings disappear. They're gone. There's no problem left, etc. So there's no triviality problem or anything. It's just the theory is somehow dissolving itself. That's very much like the case of chiral QCD. We have massless quarks in UV, non-repeating coupling run down and condense, pions are produced, etc. That's the same principle in principle, that you run a theory with fermions down and get the scales. That's actually then the guideline for the UV completion. You say, make the UV completion such that the lambda becomes the scale of dimensional transmutation, etc. So this is the diagram here. There's a first step from where we are, from the Higgs, to some scale lambda, which is something at 10 TeV, where then some condensation happens to explain the pions, in this case the Goldstone bosons eaten in the W and Z, and the Higgs, etc. These are the states. There's a spectrum of states at lambda typically, which is 10 TeV, so there are particles to be discovered, etc. And then there's this big range here, which is the conformal area, which is explained by chiral condensation. So this is the idea, and the point is to show you that this works in a nice way. There's some remarks. We did realize it for a standard model, but there's no prejudice. If you want, you can do it for multi-Higgs models or anything else, etc. It's just a generic mechanism. It can be combined with neutrino masses, dark matter, Barnard symmetry. I will say a few things then if time is left. And it can be combined with gravity, actually. That's, of course, the challenge, because if you talk about scale invariance, eventually you have to talk about gravity, and gravity has the Planck scale built in. How does that fit together? I come back to that at the end. So that's the basic idea. So first step is this little Higgs case here, this step here. The lambda is the scale of some composite dynamics, typically 10 GeV, and you want or lower. Then you have condensates which generate Goldstone bosons or pseudo-Goldstone bosons, and you have a gauge kinetic term, and then the radiative generation of the W mass and the potential. What you find then is that the mass parameter of the standard model, mu squared, is calculable this way. There's a constant order 1, g squared over 16 pi squared lambda squared, etc. And if you put numbers in these relations, then you find if you have a Goldstone boson decay constant like 200-300 GeV, that's what you need to explain the W and Z mass correctly, that the scale lambda tends to be at most 2 to 3 TeV. More like 1, 2 is possible, 3. That's the argument why you did expect some new physics at the LHC. If these are the Goldstone boson that we see, so the W and Z, then there must be new physics, lambda at the 1, 2, 3 TeV scale, which wasn't seen. So that's also is the point. And in fact, of course, the spectrum of your theory, if you have a lambda, also typically in lower-lying states. For example, if you have QCD or Technicolor, there's your scale lambda, there's your pions, but there's also vector mesons and things like that. So they would be low TeV scales. They would also have to show up. Nothing of that happened. So that's why you go to this little Higgs construction, where F can be TeV-ish, multi-TeV-ish, 5 to 10 GeV without problems, because the relation is changed to the fact that even the Higgs boson is a Goldstone boson, pseudo-Goldstone boson. The relation, and this relation gets changed in this way. There's a log popping up here. That means this lambda can then be done with 10 TeV without problems, and that's where LHC didn't test anything. This little Higgs idea essentially mitigates the problem that something should have shown up here. Then, of course, you have to worry about the high scale. The high scale is the conformal UV completion. So the idea is actually to simple, very simple. Make the little Higgs model with your fundamental scalars that you don't like. Make these scalars a Goldstone bosons of yet another dynamics and match it together. So the idea is an effective theory of a conformal completion. So you have to find a suitable conformal theory that describes the upper part. You don't want any fundamental scales up here because that would create the hierarchy problems. No scales because that would be creating problems. You only start to use chiral fermions and non-abelian gauge group, etc., which is asymptotic free. So you get a trivial fixed point, the beta function asymptotic goes to zero, etc., so that the conformal anomaly in UV is zero. And in infrared, you go a dimensional transmutation, very much like massless quarks do when you run down and get the pions and the Goldstone boson decay constants for that, etc. And the trick is to choose these fermions such that the condensation gives you effectively the little Higgs model. If you can map that, then you're fine, because then your little Higgs model solves the little hierarchy problem, and that part solves actually the big hierarchy problem together. So, as I said before, the dynamical transmutation means that there are no Yukawa couplings. Fundamentally, Yukawa couplings are lambdas beyond lambda, so there's no lambda squared corrections beyond that point anymore. That's the logic. Then you have to realize it, and that's what we did then. By just sitting down, we simplified this idea for the so-called bestest little Higgs model. It's a UV completion without elementary scalars. A confining theory, we take S to NC with NC equals 2. So the new fermions, call them technifermions for light flavors. See, those the fermions, they are representations, fundamental representation on this color group here. On the SU3 color, they are singlets. On the SU2 left, they are fundamental or a singlet representation, the hypercharge given here. You select them so they do what you want. There's the SU2 left of the standard model is actually a subgroup of the larger SU4, and the custodial group SU2 left prime, a subgroup of SU4 left prime. And the conjugate fields transform under the subgroup of SU2, SU4 right, so it's something like a left-right symmetry plus a vector symmetry. And if you do condensation, you break also the flavor symmetry, which is also interesting if you wanted to explain flavor structures. That's principally it, and it's something constructed bottom up. It's not that they have a large principle that they say that's how the world must be. It's the ideas, taking these ideas to solve these problems, what you have to do to get it to happen. And again, it's not unique because it's only one thing. There are other solutions to do the same thing. But it's teaching you how you bottom up solve the problem and avoid the problems in a way which respects what experiments seem to tell us. Then the Higgs sector is then straightforward. You go backwards from top. You have a condensation. There's 15 Goldstone bosons. They transform under the custodial symmetry SO4 in this left-right symmetric way, which is a subgroup of the vector group as this way. Then there's a Goldstone boson matrix, which can be written in this way. I think it's well known from when you do Goldstone boson expansion in this exponential form. And there's a bidoublet Higgs, I'll say, and then triplets Higgs is generally, etc. And these are all states which live in the 10 TV era, nothing to worry now, etc. But the low energy part that's left over is the standard model Higgs doublet, so say. That's it. Now you can discuss it, and I think I will not bore you with how I do this in detail. Just believe me that you can do it this way and get exactly what I described worked out. And then you ask yourself, is there anything else that you predict that would guide you? The phenomenology, so to say. So the first thing is to say that you have this 5 to 10 TV scale where there's a fermion condensate. We expect the sponners breaking of the symmetry and etc. Then the Higgs partners emerge as Goldstone bosons. So this bestest little Higgs model is the consequence. So one of them is the standard model Higgs. The other one is a triplet, is a scalar triplet. So H2, a doublet, a scalar triplet, and a single eta exist with substantial mass, at least TV or higher. That's the point that the LHC we cannot see the Higgses in the, let's say, 2 TV area yet. So these guys would be around the corner, but they're sort of hidden, so say, in the experiment, and that's why you didn't see them. But if you have more sensitivity, these guys should show up. Then there should be heavy partners to W and Z, W prime, C prime, with multi-TV masses, at least TV, etc. And then there's fermionic top partners have masses at the scale F, so say, they're also around. So in some sense, there's a promising future for the LHC for runs, but also for an FCC or another machine. It just says that the problems that we made us expect new physics to show up at the LHC translates now at a somewhat higher scale. You should see something new if that's the way the little hierarchy problem is solved. Could also talk about dark matter. The lighter stable neutral composite scalar can be a dark matter candidate, etc. That's what this model says. There's some other changes which are interesting and rather generic, which I'd like to point to. Then when we talk about neutrino masses, things change substantially. So if you have conformal symmetry on neutrino masses, then this changed a lot. There's actually emphasized because Yuri Smirnov, not the famous Smirnov, Yuri Smirnov, a young member of our group, was still looking for a career, and I hear he was here some time ago. That's the guy that was not a student here. So we said the same thing, no explicit scale for neutrino masses means that you can have, in that scenario with conformal symmetry, you have no explicit Dirac-Majorana mass term. You cannot write it down, it's not allowed. So only your Kawa couplings on generic scales are what you can do. So you can enlarge the standard model field spectrum in this way. We follow here these guys, how they did the combinatorics, which is essentially the direct product group of the standard model of some new sectors, etc. And then there's two scales in principle in a game. The one is the conformal symmetry breaking scale, and the other one is the electric scale. That's it. Everything else is so far away, etc. And it has an important consequence for the mass terms, the fermion mass terms that you can generate, because you can then have a spectrum of your Kawa couplings which either multiply with TeV scale or the electric scale. And this has interesting consequences because the Majorana mass term that everybody argues for, they are no longer expected at the generic lepton number breaking scale. They could be anywhere. Let me exemplify this with the consequences in the simplest case for neutrino masses. This is the famous type 1 seesaw. We have this 2x2 matrix where there's the Yukawa couplings, which make a Dirac mass for neutrinos here. This is the missing explicit Majorana mass for the zero, so to say. That's the Majorana mass that's generated for the left-handed guys then. Usually if you diagonalize this, then you get this Dirac mass squared over the Majorana mass as your expectation. And the expectation then is that the Majorana mass having Majorana mass is an explanation why the neutrino mass is so light, because the Dirac mass squared over Majorana mass is suppressing the mass norm. So if you have conformal symmetry, it's changing because you have the right-hand singlet, you have only this TeV and this scalars here. We expect that any of these terms here in the 2 element are no longer explicit mass terms with some lepton number breaking scale. These are a scale times your Yukawa coupling. And of course, your Yukawa coupling can be tiny. So you can easily have a scenario where this term here, actually, this 2 term is smaller than the Dirac mass. So it means that the seesaw predicts a pseudo Dirac neutrino scenario as opposed to the usual classical seesaw. And that, of course, means that you have a wide range of stereo masses, including Dirac case. You get a natural suppression of tau beta decay, even though there's lepton number violation. Here, you wouldn't see it in the neutrino masses because it's suppressed, etc., in a very simple, naive, forward-working way. And you can do the same exercise for essentially any other neutrino mass model that people discuss. The literature is full of that. And there's always the standard assumption that this Majorana mass is explicit and heavy. And it's no longer explicit and heavy when one in conformal symmetry. It can be a Yukawa coupling times a heavy scale. And Yukawa couplings can be tiny. You can do it for other scenarios, like if you do radiative masses, like diagrams like this, same thing. You get the scales here, and they get a pseudo Dirac case out of this as you do in other case. So the punchline here is the usual neutrino mass terms can be generated, as usual. There's no change. But the suitable scalars are required to make the terms to fill the matrix, but there's no explicit mass scalar. So all masses appear via your Yukawa couplings, and that means you get vastly different experimental parameter ranges that are possible. So that's why doing neutrino physics and finding a simple seesaw or finding something else is extremely powerful to tell something about such ideas. It's a check mark for these ideas to be at work, so to say. And that's, of course, happening in neutrino physics with experiments testing lepton number violation, tau beta decay. Moving forward, that's the way to go. So the best thing would be find a neutrino mass in, let's say, in Katrin type experiment and find tau beta decay, and it doesn't fit together. Then you're in business. It's one thing. The other thing is dark matter, conformal symmetry dark matter. I think there's different natural viable options, so say electron volt KeV, TeV, etc. And standard neutrino masses are possible. It's not so easy in a standard seesaw, so say, but it's possible. So the question is, are there any of the particles which you generate this way natural dark matter candidates? And the answer is yes, because you can have different ways. So the spectrum particle discussed usually has particles which have charges, they're not. But as soon as you have a hidden sector in your game, then it starts. If you take the standard model times a group where the condensation happens sort of in a hidden sector, this hidden sector still talks to the visible sector in the way we expect it via portal terms, but the hidden sector condensation produces particles which are perfect dark matter candidates. They can be hidden sector pseudo-Goldstone bosons at masses just the same masses as we have, but we simply don't see them, etc. And there's also stable color bound states from QCD type representations. So there's lots of ways to discuss about dark matter in different ways as it has been done once you enter that kind of theoretical ballpark. Some of them look like WIMPs. So if you found something like a WIMP, it wouldn't tell you it's not excluded. There's others are extremely weakly coupled via Higgs portal, so you can also have particles which are out there, even at electron volt scale. So if you can do very precise experiments where you test something more precise than before, you have a good chance. It's always the question how much investment you make, how much money you spend versus what you can learn. But it could easily be that a very small experiment which very precisely measures something at low energy finds a deviation which could be connected to such things. So we shouldn't have a prejudice here. Yeah, so that's it. Let me then spend the last time on something you should make you nervous, especially if you talk about string theory and other things. What about gravity, what the Planck scale? That's of course the problem. And I think the way to go is to be consistent, namely to do the same thing as you did for the other sector, namely that you talk about conformal gravity. Conformal gravity is a version of gravity where the Planck scale is not there, the scale invariant, etc. It's actually nice because it has more symmetry. It's actually better in some sense because normal gravity is not renormalizable, has problems. It's not a meaningful quantum field theory unless you do something in string theory. There are solutions, etc. But by itself, it's not renormalizable. If you go to conformal gravity as a quantum field theory, it's claimed to be power counting renormalizable. So you can do loop corrections like you do in the standard model. But then there's problems, I'll say. The point is that this conformal gravity may have ghost states. I will say something about this, double poles for the experts here. That would cause a stability problem, but otherwise it's also okay. So you can think of generating spontaneously the Planck scale by some dynamics. And that's actually not new in some sense. This goes back to the famous work of these people in some version. So you can think of terms like this ones where some scalars and the Ricci are connected. So say if this S picks a VEF, then you get a Planck mass essentially effectively out of that. And the Planck mass then is some coupling times this expectation value. So it would say that the Planck scale itself is not a fundamental number, it's some number being generated. So that's why we said let's do this in the ballpark of modern quantum field theory. So I did the Planck scale from a conformal gravity times an SUN. So it's a gauge-assisted condensation via this SN field to create generator Planck scale as an effective scale. So it's different people, etc., and follow that route then. And the way it goes is that you write the action, as you do, and you have the most natural construction. You have the Ricci curvature scalar, the Ricci tensor, and the Riemann tensor. After the field strength tensor of this SUN gauge theory, the S is a complex scalar in a fundamental representation of this color group. So essentially, with respect to the color group, this is scalar QCD, a scalar coupling to something like QCD running up, condensing like it would do at any scale. The point is that here it's chosen to have this SN run up, coming from beyond the Planck scale, at the Planck scale to condense, and produce a vacuum expectation value for this field S. And this means there's dimensional transmutation. There's a condensate for S dagger S, which sets the effective Planck mass. So you find that the Planck mass is then, these quantities can be calculated in this way. And then from that moment, after breaking, if you go beyond that, the effective theory is just normal gravity. The Planck scale is connected to this condensation, and far below you don't worry about the problems anymore that you had at the beginning, right? So that's the idea. And of course, you can discuss features, etc., and so on. One feature is inflation, because these days there's lots of data on inflation. They kill you. So we looked at the Dilaton-Scalaron inflation scenario. I will not discuss the details here. You have to get slower inflation and find that the data fit very well. Here you see the diagram, the usual diagrams, etc., and where we are sitting here, which is within 1 sigma of what you expect. So that's nice. Looks good and promising as an idea, but then you have to realize there's a problem, this ghost problem. So let me go back and make some comments on the ghost problem. The ghost problem is a generic problem in quadratic gravity. It's renormalizable, but then of course the point is that these dimensional numbers translate into dimensionless quantities, and the problem is then when you're on this side, then you get a double pole, which is the classical Ostrogatsky instability, namely that the propagator has this structure which is essentially a double pole, more than a pole, etc., which means that the Hamiltonian is unbound from below in the end of the day. That's a problem that you cannot ignore. So the quantum theory, even though it looks as if you can do the calculations, has a problem because there's no bound from below, etc. If you quantize the theory without taking care, it leads to sort of negative norm states and violates unitarity. So there's something wrong in the theory with these double poles. There's different ideas to go, and people discuss it. It's a long problem. It's been discussed many years. It's still under discussion, and I would say it's unclear if it can or cannot be solved. One way, actually, which I will not talk about, is to actually do what I call the Dirac trick, to make these fields respect both a second and a first order D'Alembert operator. It's like Dirac. Dirac had a problem with the fact that kinematics is quadratically relation, the energy momentum relation, while the quantum mechanics wants a linear equation. Just wrote the Dirac equation with an algebraic object and squared it to get then both relations fulfilled, which led to the Clifford algebra. I can do the same thing for gravity by saying I want both equations, which gives me an algebra. And by doing that, by squaring that, I solve the problem. That's one way to go. People work on that, etc. The ways is the potential solutions, etc. A few of them here. You can remove the ghost from asymptotic spectrum in the Lee-Wick style for the experts here. So you quantize ghosts as phacons that don't appear by definition. Some work here, or demonstrate that the ghosts are unstable with nice decay products. Means essentially that you don't care about the ghosts below the Planck scale, but above they are unstable, etc. Or you use an alternative quantization procedure. You can define a more generous quantum mechanical norm. I don't know if I would buy that, but people talk about that, etc. Or employ these PT symmetries that people find very exciting. So say this is Bender and Mannheim follow that route, and so on. And these gentlemen said that unitarity is okay if the interaction is restricted below the ghost mass. So, and they say conformal theory is okay if the ghost becomes massive after spontaneous symmetry breaking, etc. So I would say it's a long-standing open problem if these ghost problems can be solved or not be solved, half solved, half unsolved. If it can be solved, it's a strong, an important statement also, because that means you can go this route and talk about conformal gravity and embedding this way. If not, then I think then there's something else we need to talk about, other solutions which do exist, like string theory and other ideas, etc. It's also important because it would change things conceptually enormously. Because if these ideas were realized, the Planck scale is just an intermediate stop. You can go to transplanting physics. It will be quantum field theory forever, etc. No scales, and the question would be what kind of concepts would actually generate such a scenario where quantum fields describe nature, etc. That's then, if you go to the, let's say, entropic type arguments, how would that make sense from an even larger picture? I don't know. But it's very inspiring, etc. And of course, the good thing is that we have more and more data coming in, and one or the other way we'll sort it out, and the results will guide us and kill some ideas or make them more promising. So with that, I'd like to wrap it up. Let me conclude. As I said, the standard model works perfectly. There's no problems besides triviality in some sense. It is metastability. There's this list of open, unanswered questions, problems, which make us believe that physics beyond the standard model must exist. There's lots of progress on things, etc. But the hierarchy problem actually worsened because the little hierarchy problem shows up. None of the ideas of the standard old ideas that make us believe that new physics must pop up in the LHC era didn't happen. And there's in addition this remarkable coincidence of parameters that makes the potential almost go flat, etc., which also is inspiring. That's why we said, let's talk about these conformal little Higgs ideas, namely that to use these little Higgs methods to explain the little hierarchy problem, to shift the problem mitigative at TV scales, and then to complete it from the UV side with a conformal theory that makes the little Higgs model the infrared effective theory of the little Higgs model. Patching it together. Then in principle, you could say if that is the way nature goes, then it solves the little and big hierarchy problem. It's quite a claim, but in principle, it's okay. There's a number of interesting consequences, implications, and questions. So there's phenomenological implications for the trino physics, where you could learn something that points in one or the other direction. Dark matter, I think, is of course still a hot issue. Same thing there. We were for years pushing for standard WIMPs. They weren't there yet, so that's why people look in all sort of corners. And I think if you come from that perspective, there's more corners than people have been looking at, because the dark matter could be sitting in much lower masses, different parameter space, etc. way. So it's opening up the case also. So it's interesting to discuss all the ideas in connection with gravity. It's on one side very interesting and promising. On the other side, of course, there is the ghost problem, which I think is something one should continue looking at. And it's an old problem for decades, and I do not expect it to just overnight disappear. But there's a lot of intense discussion going on how this might be solved or not solved. That's, I think, all I wanted to say, and I hope you enjoyed it. Thank you.
Now we open for questions. Did you have one?
Okay, I want to start with a basic question. So I'm trying to understand how the statement that the little hierarchy problem actually makes the big hierarchy problem worse. Can you explain this again? Why?
Well, is that if you take this, let's say, scalar as the standard model as a scalar, if you go to any extension with another scalar, because then you have a second scale, and you don't understand their relation, right? That's what it is. You would expect if you do a loop calculation to the Higgs mass with new physics, with another scale in the TV range, you would expect that the Higgs mass goes up. In other words, TV squared over 100 GV squared is a factor 100. If it goes to 5 TV, it's getting a big number in the hierarchy, which you don't understand, right? That's so say the little hierarchy problem, because without the reason you would say that there's something should pop up. But that's very generic. Any of the models that people discuss essentially say there's new physics in the multi-TV range. And that's the conflict is that the LHC didn't see any of that in this range where they should see something, right? So that's why ideas where I say, can I mitigate the problem by having a mechanism that puts the new physics further away? Interesting per se, and these little Higgs models do it in a systematic way by making the standard model Higgs boson itself a pseudo-Goldstone boson. Not just that those Goldstone bosons which are eaten by W and C, but also the Higgs itself becomes a fourth pseudo-Goldstone boson. That's the trick how you can change the relation between this Higgs mass and the new scale. That's the first step that we use. And then, of course, if you do just that, then you back to the old problem, because at 10 TV you have the same problem as scalars and still problems, and that's why we say that's the trick is then, as I said, to combine by saying if that theory is an effective theory of some UV completion where the scalars you need are actually the Goldstone bosons of the symmetry of that theory, then you solve everything together. That's the idea to combine these things.
So the second question is there like simple way to construct this UV completion of standard model? Is this bested little Higgs as an example, or?
No, I think it's bottom up. So the exercise in the end, you know the Goldstone bosons of let's say of your little Higgs model, and then what you do is you say which kind of fermions do you have to choose and which symmetries to produce the right Goldstone boson spectrum. That's it, right? You can say, why these fermions? Well, that's just the bottom-up attitude. If you want these Goldstone bosons, you have to choose these fermions to begin with, right? It's like if you have 3 pions, you can say, what's the symmetry of the quarks? It's very simple. It's S to the left times S to the right, converted to S2 vector. That's it, right? So it tells you the SU2 quantum numbers. The same thing here. If you want certain quantum numbers for the Goldstone bosons, it forces you to choose the proper fermions at high scales. It's not explained. It's just a choice then.
Hi, thanks for the talk. So I was just wondering, you mentioned there's LHC and then FCC, so we have been analyzing those future colliders prospects. And if you increase the energy, that's an obvious way to look for new physics and solve the hierarchy problem. But before we get there, we're going to have the high luminosity LHC and FCC precisions. So I was wondering how those Higgs precision measurements can influence the hierarchy problem.
Well, first of all, don't get me wrong. I think the LHC and its upgrade should be done. There's an upgrade program keeping people busy for years, etc. And of course, the precision that you test the standard model is important, right? Because I think there's this argument: what's the most promising candidate or channel to go for? And I would say, especially those people that argue for a Higgs factory, say the precision measurement of the Higgs coupling, right? Any multi-Higgs model will tell you there's a deviation in the relation between the coupling and the VEV. So in that sense, is very generically a statement, I would say. So it doesn't matter if the scalars that you talk about are fundamental or composite. So precise measurement of the Higgs mass, VEV, to coupling relation is a test of any wider Higgs sector, right? And here, there's this little Higgs model, is a wider Higgs sector, 10 TeV. It's a small effect, but in principle, if you're precise enough, you could also see something there. It's the question, how precise will it be? That's the question, right? How precise can it be? But be my guest. And if you want, if there's, let's say, if you say, could it be that something shows up bigger? I would say yes. Let's so say that this relation, measuring this relation, tests if there's only one Higgs and the scales that are connected, right? And that's very important, I think. I would even, for me, I would say that's the most important measurement in the LHC program.
Yeah. Thank you for the talk. It was really interesting. The thing about the solutions involving the hierarchy problem are all related to the scale energy, right? So, scale energy. So if we don't find new physics at I don't know field TVs, the problem just get worse and worse and worse.
Right.
So what would be your idea or your feeling if we don't
Yeah.
find new physics at FCC?
That's a very good question. So we are sort of mitigating the little hierarchy problem by these little Higgs ideas, and then we solve it in a different way. Now, if you didn't find anything then with the FCC or something like that, then the problem is bigger. And then the question is, so how could it be that naive power counting, because that's what is doesn't work, right? Naive power counting. If you have quantum field theory in 4 dimensions, there's naive power counting, and by not finding anything, you would say this miraculous. So you have to talk. I would say you could talk about, could you implement a conformal symmetry scenario without intermediate layer, so that the new physics is all the way at high scales, direct from the standard model. That's, in fact, we have discussions like this. It's not easy, even though the Higgs parameters tell you something special with this vacuum stability is going on, but that idea is not easily realized, so say. But who knows? Maybe we're missing one ingredient which just changed the discussion. But I would say if nothing shows up at 10 TV, then the big problem is so big that you have to really think about the naive power counting starting from the electric theory. Can you mitigate that, avoid it the way as it's done usually? And I think the only solution then would be connected, in my mind, to conformal symmetry. That's connected to the usual power counting, right? If you have a photon propagator with a fermion loop, you say, hey, quadratic divergent. Then you say, no, forget it, gauge invariant and log divergent. And then you normalize it's finite. In the Higgs propagator, you say quadratic divergent, right? If you have no mass conformal symmetry, then you say, well, only log. But then people say, there's the conformal anomaly. Yes, but the conformal anomaly is proven to be proportional to the trace of the energy momentum tensor, which is the beta function, which the log divergence is only. So there's a good hope in some sense from that side that that conformal symmetry, even though it's broken by the anomaly, is still not completely broken, only broken by the log terms. And that's the direction we are discussing. So if you can have a realization where only the log terms pop up, the conformal anomaly is there, but that still is partially protective and kills the quadratic divergences. It's just discussions at the moment.
Okay, great. Thank you.
Further questions? Meanwhile, I do have one. So you were advocating for the idea of not having scales and not having scalars. But in the end, when you want to accommodate either neutrino masses or dark matter, then you invoke scalars. So what's the...
Yeah, scales, not scalars.
Yeah. Okay.
So scales are, let's say if you have Goldstone bosons, they condense, they're scales, not scalars.
But for instance,
there's
you
no
added-
fundamental scales, there's effective scalars, right?
But there was one of the triplet scalar.
Yeah, but that, again, so say, if you have no explicit scale allowed, let's say neutrino masses, because there's conformal symmetry, then you write the Yukawa coupling in terms of VEF, and the VEF can be an effective scalar, right? It's some of the condensating fermions that you talk about. That would be the consequence. Of course, if you then introduce a scale, you would just kill yourself, etc. at the beginning, right? But the main point is that the usual gymnastics of seesaw, etc., changes drastically because the Yukawa couplings pop up there, which can be, because of chirosymmetry, can be tiny numbers, right, compared to the normal order 1 statements.
Okay.
Gravity story also had a scale.
Yeah, absolutely, I agree. So there's also, actually, I can tell there's also some discussion on gravity doing the job. That's an interesting, very interesting remark. It's, let's say, I think experts in the field, it's not easy, so, but you have to keep trying because there is a problem inspired by observations. Right? There's something going on which we don't understand. So maybe we still miss something, or some of the ideas are not fully worked out. I think that's the ballpark of discussions.
Any?
I thank you, Manfred, for the talk. My question is in the same direction as Fernando. Like, if you have, we could have, for example, instead of the FCC, we will also have, for example, muon colliders. So in this direction, we could probe, for example, flavor of physics, something like this that usually appears in new models with Yukawa coupling, for example. So how could we probe this hierarchy problem using flavor physics?
Well, that's a complicated question, I would say. The flavor problem is a problem by itself. So, as you know, people have been talking about all these flavor models with discrete symmetries, etc., forward and backward to the point where it's getting a little bit, how should I say, frustrating. People right now are models with some flavor group and breaking sequence with flavons where more and more looks like engineered, not like a simple mechanism. Where if you look at the data, there seems to be some relatively simple pattern, right? So seems to be like you're not moving in the right direction by having more and more precise flavor models. Doesn't mean that we don't learn from that now, right? So then, of course, flavor problems usually have little to do with the normal hierarchy problem, right? That's the thing. But of course, you can easily connect them once you have a scale. You can connect them. It's in the end, if you connect flavor to these problems here, you get a very large chiral groups, right? Because it's all the generations. And that's so say for me boils down to okay, why would nature choose a huge chiral group to begin with, and then it goes to the point where the largest non-abelian groups you can write down have to be used, right? Of course, it's then connected to the fact why there are generations at all, why there are copies. We don't know. I would say nobody understands in the standard model or beyond which representations are realized by nature. It's also sometimes mind-boggling because if you look at things a while, then you find there's a pattern. In the standard model, for example, if you look at the fermion table, the full generation, you find all the combinations of singlets and fundamental representation of color, SC2, and U, etc. Right? So then if you look at this, there's only one guy missing, the right-hand neutrino. That's it. But of course, you know, when you go to guts, it's different, right? There's suddenly it's not this simple pattern of this singlet plus fundamental representation. It's different. So there's some pattern that smells like something, but it changes when you go to another perspective. And I think we simply don't know. I would say nobody knows who chooses the representations of your theory. And that's so say that's why I was saying it's hard to say what it means in the end. So you need some ideas where representations are coming from. Personally, I believe that the representation that you talk about has something to do with Planck scale physics. That's my personal intuitive answer, but we can discuss it offline. And so it means that the gauge theories we discuss are orthogonal to that problem at this level, but it's a prejudice.
Thank you for the answer. I have a broader question. It's more about the connection between cosmology and particle physics. So if we do not observe anything in the future colliders, as Vito was talking, what we would expect about how we explain, for example, the standard cosmological model, and in this perspective, for example, from the DESI new results, we have like it seems that the energy, the dark energy is it changes with time, right? So we should have some kind of explanation, not just for dark matter, for example, but in this case, how it would be connected with the hierarchy problem again.
Well, that's another wide field, I would say. It's not easy. So first of all, there's the standard model of cosmology, which is equally impressive to the point, I would say. And of course, you have to be careful how far you push it. So, say, for example, this time-dependent dark energy, I would put a question mark there. It's interesting to think of it this way and see what it can do. But in the end, do I believe if it has been established? No, I'm not. But there are, of course, important results, like the recent Atacama-Planck results for neutrino masses would mean that neutrinos are normal ordered hierarchical, which is very important in a certain sense. And now if you go and find a neutrino mass at, let's say, at Katrin directly or in Tau beta experiment, we have quite some impact, right? So that's what I'm saying. So it's all important, and it depends what you find. If you ask yourself, is it what do we know about dark matter and dark energy in the end of the day? I think dark matter has been driven by the usual standard candidates, axions, WIMPs, and sterneutrinos. They're still alive, etc., to some degree, but there's also new candidates popping up at high energy, low energy, etc. I would even think wider. So if you think about dark matter, dark energy in even wider context, there's other things we can discuss. There's people that work about modifications of gravity, not like the modified gravity in the Gilram sense, like the stupid simple things that are excluded, but you can ask the question if Einstein's observation, the equivalence principle, that you cannot distinguish a gravitational force from a other acceleration, which is cast into the equivalence principle, that's the foundation of generativity. But that's an empirical observation which at some level of precision may fail. And if you do that, you can talk about versions of gravity that are even more complex, which in the infrared limits, so say, is get back to GR. And knowing some of these theories a little bit, etc., I can tell you that it would be interesting, the interesting consequence for dark matter and dark energy in these theories as well. So we are chasing the new particles at the moment, but who knows? Maybe we are chasing the wrong thing. So we should be open-minded and just try everything, like always in science, discuss the problems, what kind of solutions, and in the end it's an experiment that will decide. That's, I think, the way it is. Anything from just around the corner, simple, to very complicated, unexpected is possible. It's nature.
Hi, Professor. Thank you very much for the nice talk. I was wondering, just for curiosity, I saw in the previous slide that maybe a strong candidate of dark matter is the pseudo-Nambu bosons. And I was wondering your thoughts about the QCD action as candidate of dark matter.
Yeah. You want me to answer that?
She was not there yet.
It was not, so I keep joking. I was shocking my students by saying, if somebody finds an axion, then I quit physics. And the reason for that is, so my personal explanation why I don't work on that, right? Doesn't mean that it couldn't be like that. And the reason is, so say, the difference when you do what I just said, like gravity, right? Or make an observation, make GR, it's nature which tells you something and inspires your theory. Equivalence principle. It gives you gravity, which is very powerful. The axion is the other way around. You see there's a problem, theta is tiny. You think about it, after something you think, well, if I make the field roll down, it happens. Then you ask that your brain is copied by nature, as opposed to copying with your brain nature, I think. So that's why I think it's asking a lot, so to say. That's why I personally like other solutions more. There's, of course, the different solutions to a strong CP problem. I personally like the spontaneous CP violation more, which can happen on certain extensions, etc. Of course, it's easily said, but then you have to work out how it works. Spontaneous CP violation is nice because it does not involve anything new. In quantum field theory, the system is going to a lower state if it's energetically favorable. Then spontaneous symmetry break is a mechanism that's there for free. So it's just a question if your theory has it built in. That's why I tend to like that. But if an axion is found, I pay the party, I will be happy, I promise you. And I will say I will feel sad that nature realized such a concept. It's my personal pressure. Don't take it personally. It's very interesting. It's just, I think you only have to explain why you do or do not work at something. Right? That's it. That's it. That may easily be wrong.
No? So let's thank this speaker again.